All right, awesome. So the plan this lecture is to finish up the composition lemma. I'm going to talk about the ZB lemma, which stands for Zalberger birthday lemma, and composition lemma. So let's recap, just so we know where we are. So last time what we showed is that for all f, and questions are welcome at any point. Don't mind the camera. For all f in Zn to Zn. Those who cannot read what I write, raise your hand. Those who can read what I write, raise your hand. Okay, all right. So for all f in Zn to the Zn, these are functions whose domains are the first non-negative consecutive integers, and the codomain is the first non-negative consecutive integers. What we said is that the automorphism group, the group of symmetries of the polynomial product I different from j of xj minus xi. I'll give this polynomial a name, but since we're in review mode, I might as well just write it. So this is x f of j minus xj squared minus here x f of I minus xi squared. So the automorphism group of this polynomial is equal to the whole symmetric group if the polynomial vanishes identically, if the cardinality of the edge set, so this is x f of I minus xi squared I in Zn, if the cardinality of this is less than n, or the automorphism group of the undirected graph. So the notation for the undirected graph was GF inverse. Now I like transpose better, but inverse is what we used last time. And then you have to remove the loop edge. Okay, so, all right. So this polynomial, this relation is the first scenario where groups are going to come into the picture. And the reason this is true is because this polynomial is a glorified edge list description. This is computing the difference of all the edges. But because we're squaring, you cannot tell the orientation of the edges. And because loop edge is going to be zero, the identically zero polynomial, you don't see the loop edge. So you remove. So here, I should say, instead of saying R equals R, I should say, you remove all the loop edges and look at, well, clearly if there's more than, so R is equal to f of R. There can't be more than one loop edge, because if you have more than one loop edge, you're in this scenario. Okay. So if you have less than n edges, this difference is going to vanish, because you're comparing n minus, at most n minus 1 object. This does all the n choose 2 differences. So if you don't have enough edges, this thing is going to be, the polynomial inside is going to be identically 0. If you have n distinct edges, then the symmetry group is the symmetry group of the graph minus the loop edge. All right. Okay. Any questions about this polynomial? This is the first time group theory comes into the picture, and groups are going to be the obstacle to something vanishing. So it's a good place to start. So this is the automorphism group of the undirected graph associated with the function. All right. Any questions? I'm always worried when there's no questions, because I'm not that. Do you want to see an example?
Sure.
Okay, all right. Let's see an example. So here's a graph. Okay, and let me name the vertices 0, 1, and 2. And of course, I'm going to put. So this is GF. So the automorphism group of this graph is trivial. There's no permutation that you can make to the vertices that preserves the function. Any permutation that I do is going to change the function. All right? So here I want to note in this example that at GF, and this is GF, is the trivial, is the identity element. The automorphism group only contains the identity element. Okay. However, I want to point out that if you look at the undirected graph, so what does the undirected graph look like? The undirected graph looks something like this. 1, so this is 2. There's an edge like this. This is 0, and there's no loop edge. So this guy is the graph that I call GF union GF inverse. It's not really an inverse because the function is not invertible. But here, the automorphism is non-trivial. There is a permutation that fixes this graph. So, okay, so there's a non-trivial permutation. So the odds of this GF union GF inverse is going to be, and let me ask for help. So let me do the hard part because it's only fair that I do some work. I'm the one. So identity is definitely in there. Any other permutation you can see is in there?
0 to.
Yeah, exactly. So the permutation that transposes 0 to 1 and fixes 1 is in the automorphism group. Okay. So the claim is that the polynomial, if I write down the polynomial that we have over there, the product of xi minus xj, I different from j, this is symmetric. It doesn't see any permutation at all, completely symmetric. So the part that's not symmetric is the part that looks at the edges. So he says, let me compare the x. Okay, so here I'm actually going to write down the polynomial explicitly. So let me focus on the edge 0. So 0, so this is 0, is being compared to the edge x2 minus x1 squared. That's the first difference that I look at. And here you can see the loop edge, information about where the loop edge is disappeared. The 0 came from x0 minus x0. So loop edge disappeared. Right? So if you take this guy to be a loop edge, you don't see the loop edge anymore. Then let's compare 0 to the other edge. The other edge is x, this should be x1 minus x2. So then other edge is x0 minus x1 squared. So this is comparing the loop edge. And then I need to compare the last two edge, which is x1 minus x2 squared minus x0 minus x1 squared. So this is what the polynomial looks like, this polynomial. And you can see that the permutations that you do, they either map edges to edges, so map edges to edges, or map an edge to a non-edge. So if your permutation is in the automorphism group, so for example, it's this, if you permute x0 and x2, you can see that basically this edge moves to this edge, x0 and x2. So x0, we need x0, right? So if I permute, what our permutation says, we can permute 0 and 2, right? So what happens? So if I permute 0 and 2, this becomes x2 minus x1.
And then the first one becomes x1.
Aha, okay. This first one becomes x1 minus x0 squared, yes? Which happens to be this guy. And this guy, x1 minus x2 becomes x1 minus x0 squared. And this guy becomes x2 minus x1 squared. Which we can see the differences have just moved around, right? So this guy just flipped these guys, so this doesn't change. And these guys just switched. So the polynomial hasn't changed. Now it's not trivial to see that if you apply any permutation that is not in the automorphism group, what you're going to create is a non-edge. So if you have a permutation that is none of these two, you're going to create an edge that does not appear in this graph. And you can actually see it in these factors. Okay, so if you are in the automorphism group, the polynomial is not going to change. But if you're outside the automorphism group of this graph, you're going to map one edge to a non-edge or non-edge to an edge. And you can tell from the polynomial because this polynomial essentially just lists all your edges. If you look at the polynomial, you can tell what your edges are. So is the example useful? This is what we did last time. So today, we're going to do some new stuff. Question? All right, so Now let's do the. If this is not clear, I recommend look at the previous video. I know the speaker very well. The previous video, I think he did an okay job. It wasn't great, not as good as me, but he did an okay job. Okay, all right. So now, what do we want to prove? So I want to prove that if you take the canonical representative of this polynomial, that means you do Lagrange interpolation and you look only on the grid, that the automorphism group is still going to be this. That the interpolant has the same automorphism group of the original polynomial when it does not vanish. And that's non-trivial. That's the so-called Zaberger lemma. So, the ZBL. So I don't want to rewrite this all the time, so I'm going to call this P subscript F. Okay. So the claim is that if P subscript F is not congruent to 0, modulo the algebraic relations xi to the n I and Zn, then, so here I should say if, and here is then the automorphism group of Pf is equal to the automorphism group of Pf bar. And Pf bar is the canonical representative. So we're going to need to review the canonical representative. Okay, so what is this saying? This says if you take the polynomial Pf, this polynomial, the degree of this polynomial in the variables is massive. I mean, this is really big. This has really big degree in each variable. If instead of looking at this polynomial, you interpolate it, and I'm going to write down the interpolation formula in a second, the automorphism group of the two polynomials is the same. There's several proofs of this. Actually, what I prove in the paper is a stronger claim, but this is enough. Okay, so let me first recall what Pf bar is. So P, okay, so recall that Pf bar is, all right, so last time we had a very fancy notation from the Hopkins School of Graph Theory, G, Zn to the Zn. And now I'm drawing a blank. Can anybody help me? What do we write from the evaluations? Okay, so currently I am on my own today. I'm saying, okay. And here is product of J subscript I in Zn minus, and then here we have this. Okay, all right, now we need to fill in the blanks. I'm trying to write Pf bar, so this is P bar. Okay, so I should do some work. So the numerator is xi minus j subscript I. The denominator has j subscript I, but now I need to fill in everything else. Any help? Any help?
Zn minus.
All right, so Zn minus, that's good. So what do I put inside the minus?
I.
Almost. This is G of I.
Oh, yeah.
Yeah? Okay, all right. I thought I made a mistake. So, okay, all right. Right, I'm using G to describe a vector of length n, okay, whose integers are 0 and minus 1. Okay, but I'm still missing something, definitely here. This was our fancy notation born in Baltimore. Yeah, exactly, we put G. And this meant, P of F evaluated at G0, G1, all the way up to G n minus 1. Yes? Does this look familiar? Those for which this looks familiar, raise your hand, including those watching on YouTube. And those for which it's not, raise your hand. So basically, this is the formula of doing Lagrange interpolation. So you plug in all the vectors, and you use the value to get your Lagrange interpolation. It's a very natural construction. some of the audience came up with this before me. So this is definitely not new. Okay, but what's new and interesting is that if the polynomial does not vanish, if the polynomial PF does not vanish, then the automorphism group of the original massive polynomial is the same as the automorphism group of this. And that's what I want to show.
Question?
Yes?
So what does that n over line means?
Oh, this line, this means take the canonical representative of the congruence class. So divide, right? So here we're working modulo these relations.
Yes.
And I want to take the canonical representative. This is what the canonical representative is. So this bar.
No, I mean the bar under the n, like.
Oh, yeah, okay, very good. Okay, thanks. So x bar n is x times x minus 0 times x minus 1 all the way up to x minus n minus 1 in parentheses.
Okay.
Yeah, this is it's called a falling factorial notation. It's used in combinatorics. I like it because it looks like the exponent. Yeah? Okay. All right, good. And please ask questions. Otherwise, it's only half as fun. Okay, so we want to prove this. We want to prove that this indeed, the automorphism group of this is the same as the automorphism group of the polynomial. It wasn't clear to me that this actually required a proof when I first wrote it, but Zaberger convinced me that it does. So let's prove this. So to prove this, I have to say something about the symmetry group. And when you look at the expression this way, it's not really clear what you can say about the symmetry group. But there's a nice observation you can notice. So PF is a multiple of product of xj minus xi, where I is less than j. So in the way we define PF, I just erased it. There was a product of xj minus xi, I different from j, in the very beginning. This is checking that the vertices are distinct. So PF is a multiple of this guy. Because PF is a multiple of this guy, this sum simplifies. I only need to sum over the symmetric group. I don't need to sum over, and that's actually the other thing that is convenient. So the reason it's useful to think in terms of Zn to the Zn is because you associate to each one of these basis elements a function. And if I was thinking about vectors, it's much harder to say sum over the symmetric group. And this is a useful thing. So so P is a multiple of this, so this implies that PF bar is the sum over sigma and Sn, all right, of, let me write for now, P F evaluated at sigma. This should be reminiscent of the determinant formula. Product I and Zn. And then inside, I have here product J subscript I and Zn minus, this is now sigma I, and here is xi minus xi minus ji, and here is sigma I. All right. So we've reached a point in the talk where you have to be very careful. Usually, this is the time when I make a mistake. So please, catch me if I'm dishonest about anything. The only thing that changed between these two expressions is that instead of summing over the symmetric, over the whole set of all functions, I'm summing only over Sn. And the reason is, every time that the evaluation of G repeats, this thing is going to be 0. Therefore, P of the thing will be 0. So the only non-zero that can occur over Sn. And Sn is a group, so that's going to be useful for us. All right? So far, so good? Okay. So now, I actually want to understand what happens if I start permuting the variables in this expression. I want to understand what happens if you start permuting the variables. And to see this, I'm going to rewrite this sum and make this guy explicit. So this is sum over sigma in Sn. Okay. And this PF now, I know, I'm going to write exactly what it is. This is I different from J. And here, this is going to be sigma J minus sigma I. That's the evaluation part. Here's the edge part that I'm going to write as parentheses sigma F sigma inverse of J minus J, this thing squared, minus sigma F sigma inverse of I minus I squared. And now I can put the Lagrange basis. So let me call this Lagrange basis polynomial L sigma inverse. This is what I'm calling, this part here is what I'm calling L sigma inverse. So what I've done here is to expand this sigma. Okay. There are a lot of moving parts, and I'm assuming we are completely masters of the previous video. Is it clear why I'm allowed to put this sigma in the middle? Right? This is sigma. I'm evaluating our polynomial PF. I'm evaluating the polynomial PF at sigma. So this part is easy to see why. What's tricky, where it seems I'm pulling a fast one, is here you would expect that I would write sigma F of J minus sigma of J. This is what you would expect. And here you would expect that I write sigma F of I minus sigma of I. But somehow I'm able to put a sigma inverse in the middle. Any idea why? Yes?
I think you did like a change of variable.
That's exactly. And because the product is commutative, it doesn't matter the order in which you... But this has a very nice interpretation. Because what this is telling me is that if each of these is P evaluated, you can basically pull the sigma down. Right? This part doesn't change. So this part I can replace by product of J minus I. Sigma doesn't, this part is symmetric, so this part does not change. Okay, so let me write it. So we're on the same page. I don't want to pull a fast one on the very last season finale. All right, so let's do it carefully together. So this sum that I just wrote is a sum over sigma in Sn. And then I'm going to write product I different from J. But I claim that here I can write J minus I. Why? Why can I write here J minus I?
Because it's a
Yeah,
permutation.
exactly. I can use again the change of variable argument. It's a permutation. This is symmetric, so it doesn't care how you renamed it. Okay, good. However, this part here is really nice. It makes the whole expression look like P sigma F sigma inverse at identity. Right? Because as soon as, okay, so let me write it so we can see. Okay, let me write it so we can see. So here is product I different from J. We said this is J minus I, so this is the identity. And here, what are we looking at? We're looking at sigma F sigma inverse of J minus J squared minus sigma F sigma inverse of I minus I squared. This is what we're looking at. So this is as if I'm evaluating X sigma F sigma inverse of J minus Xj minus squared, and here X sigma F sigma inverse of I minus Xi squared. Right? Okay. And that's why I'm saying this expression that I write here, so this thing is multiplied by L sigma of X. Okay. So I'm saying this expression is really writing sum over sigma in Sn of the P sigma F sigma inverse evaluated at identity.
Also time double.
Yeah, of course, absolutely. Yeah, definitely. I'm just making sure we agree with this part. Times the Alex. So I actually want to write this down now. Product I is N. Product J I and Zn minus. And here it's going to be sigma I. And this is X I minus. Here I could use help. Anybody remembers what I should put here? Okay, so let me do some work. So this is Ji. What do I put here? Sigma. That's correct. So what's nice about the expression is that somehow everything is happening on the bottom. This sigma inside is basically being pulled on the bottom. That's really convenient. Now we can say, okay, what happens if I act by some permutation on the variables? Can I say what it's going to do to the expression? Okay, all right. So now if for some gamma in Sn, we permute by gamma the variables of P, of Pf, we get something quite nice, actually. So let me do the permutation. So where should I do the... Okay, so let's do it here. Sorry, we're always interested in Pf bar. Pf bar, let's see what happens. Okay. So we get something quite nice. Let me write what we get. Let me ask for some guesses. Any guess what we're going to have? It's always easy to guess after I write it down. So let's try to guess before I write it down. So if you do the permutation, what you get is, if we do permutation gamma, I'm going to, for convenience, take gamma inverse for every gamma on the variables of Pf. We get, okay, and here I write what we get. So we get some sigma in Sn. And here, I'm going to do it in slow motion. So I'm not going to do everything at once. I do. And now I'm going to write product I in Zn, product Ji in Zn minus sigma I. And now I need to write here x gamma inverse of I minus J subscript I, sigma I, J subscript I. You can guess, half is about change of variables, but we should take a commercial break. Commercial break is now. All right, ready? Okay, so as I was saying, the half of these arguments are about change of variables. And always we're changing the variables to make our variables easy to understand. So here we want xi. I don't want sigma I. Okay, I want xi. But if you want xi, the gamma inverse is going to come in the bottom, so to speak. Okay, so I'm going to write, and we'll see. So this expression that I wrote is what happens when you apply the permutation gamma I to the variables. And I claim that this is going to become sum over sigma in Sn, P gamma sigma F, parenthesis, and here is gamma sigma inverse applied to identity. And here is product I in Zn, and here is product Ji in Zn minus. And now this is gamma of sigma. Okay, and we have to check, right? You have to check with me that it's gamma of sigma and not sigma of gamma. It's one of the two. Okay, and I get confused sometimes between which one it should be. Ji, and this is gamma sigma I minus Ji. Okay. Are we in agreement? What in the world happened? So remember, I'm trying to get xi. So I sort of need to do a change of variable. So I need to change every I into basically gamma inverse of gamma of I. That's the change of variable I really want to make. So using I is confusing. So maybe I should call it another. I should do this. I should call it U and V. So this will make it easier to follow. So let me call this U. Let me call this V subscript U. Let me call this XU, JU, and then JU. And then here, I'm going to need your help to find out whether it's gamma sigma or sigma gamma. Okay, all right. So what I want, of course, I want X gamma inverse of I. I want it to be XU. So I need to propagate this change everywhere else. Okay. So what does this tell me about I? What does it say about xi? What does it say about I? So basically I'm saying gamma inverse of I is U, right? Okay. So this means that I has to be replaced by what? Gamma U. Okay. Which means this is not correct, right? It should be sigma of gamma U, right? So, okay, so let's change that everywhere. So this should be sigma gamma U. This, of course, was to check if the audience is listening. Sigma gamma U. And here, this should be sigma gamma F and sigma gamma inverse. Yes? Okay. Now, what's interesting about this is that what I've done, basically, is to permute the coefficients. This initially was a sigma. And a permutation on the variable induces a permutation on the coefficients, basically. Okay. All right? Now, here's what's important. If gamma is in the automorphism group of the polynomial, if gamma is in the automorphism group of the graph, of this undirected graph, then this, so when gamma, so let me write that here. When gamma is in the automorphism group, gamma does not change your function. So note that if gamma lies in the automorphism group, odds of GF union GF inverse, then P sigma gamma F gamma sigma gamma inverse evaluated identity is going to be P sigma gamma sigma F sigma inverse evaluated identity. Yeah? This is just because this is sigma F, gamma inverse, sigma inverse. This is gamma here. This doesn't change the function. I replace it by F. So you have this nice identity. So when gamma is in the automorphism group, basically nothing changes on the coefficient. You don't change the value here. Okay. Now, the other thing to note, which is really nice, is that whenever P does not vanish, it takes a single value. All these non-vanishing coefficients are the same. So all non-vanishing coefficients. So when P sigma gamma sigma F and here is sigma inverse evaluated at ID is different from 0, we know actually the value that is going to be. The value is always equal to the product of j minus I different from j squared minus I squared. Always equal to this. Whenever the polynomial does not vanish, it's because the vertex labels are distinct and the edge labels are distinct. But if the edge labels are distinct, you get all numbers, and the vertex labels are also all numbers. So when your polynomial does not vanish, the coefficients you get are the same. They're all the same. So now this is important, because it's saying that what my permutation does is just permute these equal coefficients. When you permute the variables, what you're doing is flipping the coefficients. Okay. Once you notice that, it's a home run. Why? Because the automorphism group of each of these basis elements is trivial. Okay. Note that the automorphism group of L sigma of X is only made of the identity element. It's only made of the identity element. Each of these sigmas, they are different. So if you stare at the denominator, you can actually recognize your permutation. If you look at a Lagrange basis polynomial had these xi minus ji, and has this sigma I minus ji here. So if you stare at all the denominators, you can actually tell what the permutation is. So there's no permutation of the variables that would fix the polynomial in the product. So the L sigma, let me write what the L sigma is. If it's not clear, recall that L sigma of X is the product over I in Zn. And here is product of Ji in Zn minus sigma I. And here is xi minus ji, and here is sigma I minus j. Because sigma is a permutation, the automorphism group of this is trivial. If this was the identically zero function, it's not true that the automorphism group of the basis is zero. So this is really because the function is over permutation and each one of these denominators is different, that I know that the automorphism group is trivial. So, if the automorphism group of each one of these guys is trivial, and permutation only exchange the coefficients, then the automorphism group of the polynomial as a whole are permutations that are mapping the coefficients to another coefficient. So any permutation that exchange the coefficients is a permutation in the automorphism group of the canonical representative. So to be a permutation in the automorphism group, what you have to do is do a permutation on the variable, and it induces a permutation on the coefficients. We saw that if you are in the automorphism group, then that happens. If your permutation sigma is in here, that happens. And what I need to do, I need to convince you that no other permutation can do that as well. Okay. So the only permutations that are going to permute the coefficients have to form a group. The permutation, the automorphism group of the canonical representative has to be a group. All right? So let's write that somewhere. Okay, so note, by definition and by construction, ought of PF bar is a group. I mean, it's closed under composition. You take a permutation and it permutes the coefficients. Two permutations that permute the coefficient. If you compose them, you permute the coefficients. Okay. Now, what's wonderful about our listing is that the listing says the group has to be the support. I mean, the biggest it can be is you're lucky, all right? So the way we're looking at our expression, the expression looks something like this right now. It looks something like product over sigma. Okay, so let's actually write the expression we care about. And we can look at its group. So here's the expression we care about. All right, so here we go. P F bar. This is the actual expression PF bar, the actual expression for PF. So this is going to be the sum over sigma in Sn, such that, so which permutation is it not going to vanish? So such that sigma F, sigma inverse, this graph, is gracefully labeled. These are the only permutation on which our polynomial will not vanish. Right? So on these permutation, I'm going to have the same constant c. Every time that the polynomial does not vanish, the constant is always the same, it's c. Okay. Times now this product over I in Zn, and here's product Ji in Zn minus sigma I. And here is this so-called xi minus ji, and this is sigma I minus ji. Okay. This is the actual canonical representative. This is what it looks like. The same constant multiplying these guys. Now, if this subset actually forms a group, then that's the symmetry group. Because remember, permutation of these is permuting the coefficient, but the coefficients, they're all equal. So what you want to know is, this subset, does it form a group? If it forms a group, that's the group. If it does not form a group, then the best you have is the automorphism group of your original polynomial. So you want to know, does this form a group? And it turns out that if the graph admits an ungraceful labeling, it does not form a group. But if the graph has no ungraceful labeling, it forms a group. So are there graphs that have no ungraceful labeling? Absolutely. Here's a graph. No matter which permutation you make, all the labelings are graceful. Any permutation to this guy. Okay, so if for this polynomial, the group is the whole set. Okay, but if your graph admits an ungraceful labeling, so let's take this, let's put here 0, let's put here 2, then it tells you that if you start with f being the ungraceful labeling, the identity element would not be here. If your graph has an ungraceful labeling, and you took gf to be the ungraceful graph, right? Then the identity element cannot be here. Every permutation that makes the graph graceful has to be different from the identity element. But if the identity element is not in the set does not form a group. And if the set does not form a group, it's not closed under composition because you can power an element and get the identity. And if it's not a group, then the largest automorphism group has to be out of basically PF. That's the best you can do. Because we saw that odd PF fixes these coefficients, and doesn't mess anything. Any other permutation, eventually if I compose them enough time, I'm going to reach identity. Therefore, it cannot be inside. The only permutation that are safe are permutations that are in odd PF. And odd PF, we said previously, is odd GF union GF inverse. And this completes the proof.
Question?
Yes?
So you said that if G is graceful labeled, then
if G admits an ungraceful labeling, then you could take F to be that ungraceful labeling. And if you do that, then it's clear that the identity element is not in your listing.
Yes.
If the identity element is not in your listing, the listing does not form a group.
Yes.
Because you can compose any element you pick. Any element in your listing, you can compose it enough time to get to identity, which takes you out. Groups have to be closed.
So, like, if G does not, if G admits a graceful labeling, then is it possible that we have a normal subgroup instead of the whole thing?
No. So in either case, if you assume that G has a graceful labeling, then you will have identity here, right?
Yes.
Okay. But I claim that the group that you have does not depend on the labeling. The automorphism group of the polynomial should be completely independent of the labeling. The automorphism group of the graph does not depend on the labeling. If you put 0, 1, 2, or 2, 1, 0, that does not determine the automorphism group of the graph, right?
Yes.
And so too is the variables. The way you name the variables should not determine the automorphism group of the graph.
Oh yeah.
So without loss of generality, you can assume that F is non-graceful. I mean, the labeling is ungraceful. And that gets you, if you happen to pick a graceful labeling, then identity is there, but there's some different reason why this is not a group. It's easier to see that it's not a group if you pick an ungraceful labeling. And without loss of generality, as long as the number of vertices is bigger than 2, every graph has an ungraceful labeling. If you have more than 2 vertices, then you necessarily have an ungraceful labeling because you can always create 1, 1 by putting consecutive numbers. Right? So if you have 2 consecutive edges, you can always do this. 1, 1. So as long as you have more than 2 vertices, there is an ungraceful labeling. Okay. So the technical part, the only difficult part is to realize that this set does not form a group if your graph has an ungraceful labeling. And if this set doesn't form a group, the support here cannot be invariant under permutations which are outside the natural group. Any questions? No questions? Or if questions come later, that's perfectly fine. But this is the ZB lemma. So what is the importance of the ZB lemma? ZB lemma says, if you know the automorphism group of this massive degree polynomial, I mean, this polynomial has degree so big, it's even hard to write it down. If you want to know its automorphism group, just keep track of the canonical representative. Canonical representative is much smaller, much nicer, well-behaved polynomial. You look at it, you study its automorphism group, you know the automorphism group of PF, the larger one. And this connection between the 2 polynomial is what's needed in the composition lemma. So now we're ready for the composition lemma. And something tells me I'm not far from out of time. So what does the time oracle say?
Can you have like 10, 11 minutes?
10 minutes for the CL. Oh my goodness. All right, I will at least set it up. And then I'll write the last line of the proof. That's a joke. Okay, all right. So what does the composition lemma say? Composition lemma says the following. So for all f in Zn to the Zn, subject to f being a functional tree. That's what we call functional trees here, but this is not standard name. I have not seen the term functional tree, and there's reason to suspect it was born here. Anyway, if f is a functional tree, then the maximum over all permutations of the cardinality of the edge labels, sigma f, this cardinality is always smaller or equal to the maximum over sigma Sn for the maximum cardinality. So of the maximum of the cardinality of sigma f, sigma inverse of I, minus I, close the absolute value, I and Zn. As I said, I don't think the proving this is hard, and the proof that I have basically exhibit all the biases of my training. I'm very convinced that somebody in the audience is going to come up with a very nice short proof of the inequality, but the hard part is to know that this is what you need to prove. Okay, all right. So this is the composition lemma, and we discuss why this is enough. If this is true, a wonderful thing happens. So the way we're going to prove this is by as follows. So we show proof. And this is the part where I really want to be careful. I'll do everything slowly here. And unfortunately, managed to run out of time, I promise. So I want to show that if PF is congruent to 0, modulo these algebraic relations, xi to the n I in Zn. I want to show that if this is congruent to 0, then this necessarily forces PF2 to also be congruent to 0. PF2 to also be congruent to 0. What I mean modulo the same algebraic relations. Mod xi n and I in Z. Which is completely equivalent to this statement here. And I have to explain why it's completely equivalent. So the thing I'm going to be able to do is to say that if you are a tree, the maximum has to be n. A tree cannot have less than n. The maximum cannot be something at n minus 1. Okay. And then it's all about focusing on PF being congruent to 0 or not. So this statement is just saying that PF bar congruent to 0 implies that PF2 bar is congruent to 0. Okay, now, how do I know that maximum cannot be n minus 1? Okay, so this is the last thing I can do. How many minutes do we have? What is
7.
it? 7! Oh, 7 is too much. I think I can slowly erase. Okay, so why can so if you assume that there exists some g in Zn to the Zn, and gg a functional tree. So if you assume that this maximum, the max of sigma in Sn, in this cardinality, so here is sigma g, sigma inverse I, minus I in Zn. Okay, so if you assume that this cardinality is smaller than n, okay, then you look at the sequence G composed with itself, G composed with itself, this guy squared, and you reach the star. Okay, so if this guy had less than n, there has to be one of these for which this inequality is false. Right? Because the star has n labels. And this guy has less than n labels. So there has to be one guy here that violates the inequality. Because somewhere the inequality has to be violated. So if this is possible, the lemma is false. Okay. All right? So I'm going to show that the lemma is true. All right? I'm going to say, well, okay, if I prove independently that this is true, PF being 0 forces PF2 to be 0, it basically establishes that this cannot occur, and therefore the maximum for every has to be n. Yeah? The problem is, this statement is incompatible with the lemma. Either this statement is true and the lemma is false, or the lemma is true and this statement is false. The two are not compatible. So I'm going to say, okay, I'm going to prove that the lemma is true. I'm going to prove this. And this implies that this is false. All right, so it suffices to focus on, basically all of this 7 minutes is a way to say it suffices to write maximum is n. I can write maximum. Okay, that's all we have time to do. My goodness, it's not season finale. So that's where we stop.